In this video, I will talk about the bond formations in the coordination chemistry. But before going on the coordination chemistry, I want to talk about other theories. So first theory is the Lewis bond theory, as you know. John Lewis introduced the theory to explain the bond between the atoms, and Coyle introduced the octahedral, the famous octahedral. From 1928, 1930s, Pauling, who's the person that introduced the Pauling exclusion principle, so it might be very familiar to you, wrote a paper, and the name of the paper is On Nature of the Chemical Bonds. And this paper introduced the valence bond theory and the hybridization concept. Around the same time, many people, Friedrich Hunt, Robert Millikan, John Slater, John Lennon Jones, and these names might be very familiar to you. These guys introduced the molecular orbital theory, but the theory name was actually Hunt and Millikan theory at the beginning. Then Millikan introduced the word of orbitals. Then the name became a molecular orbital theory. And this theory well explains the many concepts: diamagnetism, paramagnetism, color of the molecules, and some spectroscopic properties of the molecules. Then Erich Hünkel in 1931 explained the benzene. So stabilization of the benzene was explained by Hünkel by using the pi orbitals. So it's very famous again. By 1950s, molecular orbitals were completely defined as eigenfunctions. So this is the theoretical background. However, molecular orbital theory cannot explain the coordination chemistry fully. So we need other two theories. One of the crystal field theory and the other is ligand field theory. In 1930s and 1940s, Hans Bethe is the physicist, and this guy introduced the crystal field theory. After the crystal field theory, also ligand field theory was developed to explain some other things, since crystal field theory also is not enough to explain all the coordination compounds. So we can continue. Firstly, what should we know before continue? Firstly, we have to know electronegativity and electropositivity. So here we have to compare electron density and the bonding strength of the ligands, since ligand strengths depend on the electronegativity. And for instance, we can think of octahedral complex. We have a metal atom and we have the ligands, and the ligands has an effect on the complex, and it is explained by simply electronegativity. Then we should know the Lewis-dot structure and MO diagrams, as I mentioned. Lewis-dot structure is not very important, but for instance, you should be able to draw the, for instance, CO molecule. CO is natural ligand, and the CN is -1 negative charge. And CO binds from the carbon side. It binds from the carbon side, but CN can bind from the N or C, and it can be proved by the some infrared experiments. But these are the details, and we will talk about them. To know the organic line notation, for instance, you should be able to draw the organic molecules. For instance, this is CH3, CH, CH, and there is a double bond between the other. This is a double bond, right? And we can give another example, for instance this. So there are carbon atoms here, right? There are carbon atoms, so we can write them, this molecule, something like this. And then we definitely know the molecular orbital diagram. Why should we need the MO diagrams? Since all discussions depend on MO diagram. We explain the bonding, paramagnetism, diamagnetism, other important things. For instance, octahedral splitting, and I will show it in a moment. Optical properties, MO diagrams can explain the optical properties and also reactivity. Therefore, in this course, we need to know molecular orbital diagrams. So can we use the valence bond theory for the complexes to explain their shapes? For instance, we know that we can explain the shape of the methane, right? This is methane. We have 4 carbon valence electrons. So we have 2s orbital, we have 2p orbitals here, and we have 4 electrons. And to make the bonds, simply we create 4 sp3 hybrid orbitals. We put the electrons on the carbon here. So carbon has this kind of hybrid orbital, and hydrogen comes to the hybrid orbitals and makes bonds. And this is the tetrahedral geometry. Can we do it for the same thing for palladium Cl4 2-? So palladium is 2 plus here. If you ask why, since Cl has -1 ion, right? So it donates 2 electron and it has -1 charge. In this case, we have 4 Cl minus ions, so we have 4 minus charge. Palladium is actually D10. However, it has to be +2 charge to obtain -2 charge in the complex, right? In this case, it should be D8 system. So I want to clean this part, and I will fill 8 electrons. So we have 8 electrons. To make the bond, I should put the other electron here, right? And I will delete these 2. I will create 4 hybrid orbitals. And what is the hybridization of these orbitals? It should be sp2d, since I used 1d orbital, 1s orbital, and 2p orbitals from the higher orbital levels. So we have to assume that Cl, as I mentioned, Cl minus have to donate 2 electrons, and these electrons goes to here, right? And we have 4 Cl, and that should be 8 electrons. So we could make the bonds. The problem is that valence bond theory failed, since it is nearly same thing here, and the geometry should be tetrahedral for this complex, right? But this is not the case, since this complex has square planar geometry. It cannot explain the event, and therefore we need a crystal field theory. And we can use them for octahedral complexes, tetrahedral complexes, and square planar complexes also. But the most common one is the octahedral complex that you should encounter first if you look at a book. So what is going on in the crystal field theory? Firstly, crystal field theory treats ligands as a point charge. So around the metal ion is ligands as a point charge, and interaction between the ligand metal is purely electrostatic. And this is the negative side of the theory a little bit. And sp orbitals are not significantly affected by the ligands. D orbital splitting is responsible for color, magnetism, and the reactivity. Ligand field is assumed to be static and symmetrical according to the geometry. So geometry affects the ligand field. And crystal field theory does not count the electron repulsion, and it's one of the problematic part of the crystal field theory. And I want to make the Octahedral splitting diagram. Firstly, we have a d orbitals. This is the energy diagram. We have d orbitals. This is, by the way, metal d orbitals. And ligands, due to the electron-electron interaction, causes little bit increasing of the d orbitals. And this d orbitals splits into the octahedral complex. So we have two orbitals here, which are the z square and the x square minus y square orbital, and we have three other d orbitals, the z square, the xz, and the yz. So these are called as T2G orbitals, and these are the EG orbitals, and these are the symmetry. These are comes from the symmetry, but I will not talk about the symmetry elements right now. We have a octahedral splitting. This is the octahedral splitting. We have a stabilization energy. So it is plus 0.4 times the electron number in these orbitals. So this part 0.4 and this part 0. Sorry, I made a mistake. This is the octahedral splitting. However, this part should be plus 0.6 and this part should have minus 0.4 octahedral splitting energies. Okay, and I want to write the crystal field stabilization energy. So minus 0.4 times number of electrons in the T2G orbitals. So here in the T2G orbitals plus 0.6 times y. So for instance, if you have a D1 system, then it becomes 0.4 times 1 plus 0 minus 0.4 stabilization energy. And it continues. You can calculate them. For the D10 system, it basically becomes 0 since we will have 4 electrons here in the T2G orbitals and we have plus 0.06 times 4 electrons in the EG orbitals and it will become 0. The problem of the crystal field theory, as you increase the charge, coordination bond increases, and which is wrong, since crystal field theory does not consider the weak ligands and strong ligands. Therefore, we have a ligand field theory, a little bit developed form of the crystal field theory. But what does it mean, the weak ligand? For instance, we have nickel NO3 okay, we'll put it to the water. What happens? We create a nickel complex with water, and if we pour, for instance, sodium cyanide, what happens is that cyanide ions remove the water molecules and this molecule occurs. And this is not a back and forth reaction, so there is no this kind of reaction. It's just one-way reaction. Why? Since cyan is a strong field ligand, but water is not. In this case, we need a spectrochemical series, since the ligands are different from each other. If you write the name on somewhere, on Google for instance, you can see the Spectrochemical Series. I can write a few of them. For instance, CO is a strong field ligand, CN also strong ligands. In the moderate ones, PPY, EN, or NH3, or the phosphate ligands also. And we have weak field ligands. And these are the strong field ligands. And ligands affects the octahedral splitting. If we have a strong field ligand, it causes higher splitting energy. Therefore, generally, strong field ligands causes the low spin complexes for the octahedral geometries. On the other hand, if you have the weak field ligands, then the splitting energy drops. High spin complexes becomes possible due to the weak field ligands. So I want to mention also other important thing on 18 electron rule. But firstly, we need to draw the, for instance, octahedral complex, right? This is octahedral complex. Why these complexes have generally 18 electrons? So we have d orbitals, for instance 5d. We have 4s orbital, and we have 4p orbitals, and we have 6 ligand orbitals, 6 degenerate ligand orbitals. What does it mean, degenerate? It means they have the same energy. So these terms are important in organic chemistry and also coordination chemistry. So this ligand energy decreases. It completely fills all the electrons. Since we have, how many electrons do we have? 12 electrons. Since we have 6 ligands, each of them donates 2 electrons, which means that we have 12 electrons. Then octahedral geometry causes the orbital splitting, as I mentioned. We have T2G orbitals and we have EG orbitals here. And this is the octahedral splitting, by the way. And if ligand is strong, for instance, if the ligand is strong, then it increases and goes to here. I am a little bit exaggerate. If it is weak, then it goes here, and octahedral splitting energy decreases. These two T2G orbitals are nearly non-bonding, and if we fill all the orbitals, so 6 electrons, the molecule will be stable, right? Since these other orbitals are anti-bonding, and filling of these electrons causes to decrease the stabilization of the complex. So if you look at the total electron number, it is 18 electron. So therefore it is called as the 18 electron. And we use the crystal field theory to explain the diamagnetism and paramagnetism. For instance, palladium Cr4 2- is a diamagnetic molecule, so there is no unpaired electrons. By the way, both of them is the 8th system, right? But on the other hand, nickel Cl4 is paramagnetic and there are some unpaired electrons, right? This means that there are some unpaired electrons. How can you explain it? Since if you look at the valence bond theory, what happens? it will be sp2 dehybridization, and valence bond theory will fail to explain magnetism of the molecules. So in one of them it will be right, but for the other one it will be wrong if you use the valence bond theory. The problem of the valence bond theory, it doesn't count the effect of the ligands. So what happens is that basically we have different d orbital splitting here. So in the palladium Cl4 case, we have square planar complex, right? And we have square planar splitting. So we have dxz, dyz, dz square, dxy, dx square minus y square. So this is our splitting energy, square splitting, and this is the energy level of the d orbitals. On the other hand, if we look at the nickel Cl4 2 minus, so this is 2 minus, both of them is D8 system. The splitting will be tetrahedral, and this is the tetrahedral splitting. We have Eg orbitals here, we have T2G orbitals, and as I mentioned previously, due to the low splitting of the tetrahedral geometry, all the complexes will always be high spin. And if we put the 8 electrons, for instance, right, we have to put electrons to understand what's happening here. We have 8 electrons, 1, 2, 3, 4, 6. So there is no unpaired electron, therefore this molecule is diamagnetic. But if we look at the nickel complex, 1, 2, 3, 4, 5, 6, 7, and 8. There are 2 unpaired electrons, so it is paramagnetic. Therefore, crystal field theory explains the diamagnetism and the paramagnetism of the molecules. And we can go some examples for the 18 electron rule. For instance, this is a good complex, I think. We have phosphate, we have CH3, we have CO. For instance, if we look at the ligand, CO is a ligand that the charge is 0 and it donates 2 electrons. For instance, PR3 is again a true ligand, so this is the charge, okay, and this is the donated electron number, so it again donates the 2 electron. If you look at this one, for instance, it has 0 charge and it again donates 2 electron, right, since we have 2 electron here. CH3 is an important example, but I should make this thing a little bit smaller. So we can look at the CH3 minus, so it donates 2 electron and the charge is 0. Okay, that's all for this molecule. And this is a D7 system, and we should, it has a -1 charge. The metal has D7 system. If you look at the periodic table, you can see that. Is it a 18 electron system? I will write all the molecules, okay. And by the way, this is a natural, of course. So CH3 donates 2 electron. It has -1 charge. CO 0 charge. it donates to electron. We have two of them, right? We have one CO here, the other CO here. We have also two PR3. Both of them donate to electron. They have zero charge. We have an organic compound, it donates to electron and its charge is zero. And we have a central metal atom. In this case it should be +1 since the total charge of the molecule is zero. So molecule itself is neutral. Therefore D7 system becomes D6 system, and if we add them, this number 6, 6, 6, so it is a 18 electron system. And we can look at the other molecules. For instance, a sandwich complex. So we have a complex. So this is a cyclopentadiene or CP. So it has -1 charge and donates 6 electrons. So C6H6 has -1, no, is neutral, and it donates again 6 electron. The metal should be +1 since the complex is neutral. Again, it donates 6 electron. Therefore, we have again an 18 electron molecule. So molecule follows the 18 electron rule. We can make a more complicated example. So we have molybdenum, a bridging Cl. Again, we have bridging Cl. We have CO, this kind of a molecule. So count the electrons for the metal center. How can we do that? Firstly, we should look at the Cl. So it has 8 electrons, right? And it donates 2 electrons for each metal center. And due to the Cl, it has a -1 charge. There is no other Cl atom. We have 2 Cl- and 2 molybdenum. To make it the neutral, molybdenum becomes +1 charge, which makes it D5 system. So 5 electrons will come from the metal center. So we have to keep it in mind. Then I will count the electrons. It will bring 2 electrons. Molybdenum give 1 electron and the other molybdenum give 1 electron here, right? Ci gives 2 electrons. CO is natural ligand and donates 2 electrons. This is a natural ligand and denotes 2 electrons. CO also denotes 2 electrons. So I have to count 2, 4, 6, 8, 10, 12, 13. So 13 electrons will come from the ligands. And 5 electrons will come from the metal center. So it is again 18 electron system. And if you have a question, write on the comments. In the next video I will make more examples and I will give also more information about the coordination chemistry. And thank you for your attention.